Hi guys, welcome to this Wintellect webinar. We're pleased to bring this one to you, making the most of microservices. So I'm Blaze Stewart, I'm architect at Wintellect, and we are now a part of the Atmosera family, which is a recent merger of the two companies. And so we're doing this not just as a Wintellect webinar, but as a Wintellect and Atmosera webinar. And we will be presenting these in the future as kind of co-branded webinars as well. But just a little bit about who I am. I'm Blaze Stewart, architect. As I said, I'm a Microsoft MCSE, Microsoft MVP MCT. So I focus a lot on Azure, and I focus a lot on app dev as well as apps and infrastructure. And so I deal with microservices quite a bit, and so it's a lot of what I do. So I'm happy to talk about this, and hopefully this will be some helpful information for you guys, and will be something that you will be able to use in your work. So let's talk a little bit about Wintellect. Wintellect, we probably need to update this slide with our new offerings now that we're part of Atmosera. But in any case, Wintellect we're traditionally been a consulting and training company, but now with Atmosera, we have a service partner where we do managed services for folks who want to put their work on workloads on Azure. So we provide training on Azure, consulting services on Azure, and now we have a hosting service that we can bring to the table for folks that don't want to manage their workloads. They just want to focus on the business side of the things, and we can help with that as well. So almost a full service offering on those as well. So let's talk now about microservices and what that is. We got a lot of stuff to talk about today. So if you have questions, there's a question feature with GoToWebinar. Post your questions there, and I will get to those at the end the best I can, and we will try to answer those. I would save some time for the end for that, and if we go over, I'm glad to do that. I'll glad to work with you guys on that. But we'll be answering those, and this will be recorded, and we'll be posting it on YouTube. Those are common questions we get, and if you want this deck as well, I'll be glad to provide it. Just shoot me an email, and I'll send you the deck as well. So let's get started and see if I can get this thing to work here. So there's my picture. Hi, that's me in the upper right corner, and I'm presenting, trying to use some new tech. So if this gets a little flaky, it's going to be because I'm trying something new a little bit on these webinars too. Just trying to grow my own skills. Okay, let's get into microservices now. So what is a microservice? Microservices, as a definition, it's hard to get a good definition what these actually are. So what I'm going to try to do is describe these things to you. Basically, what a microservice is an autonomous service that, if we were to think about this in terms of a traditional in-tier application, we would have multiple tiers in our application. In tier, we're talking about traditional monolithic applications where we have all of our software deployed as a single set of single deployed application, usually on a single server, maybe a separate server for the database. But you typically have modules in that, and those modules talk to one another. And that model worked well for on-premise applications that were serving hundreds, maybe thousands of users. But as we went to the web and people wanted to start servicing millions of users and scaling their applications beyond what was possible with a single server, they needed to come up with a way to manage that, to make their application hyperscale or span multiple geographies and beyond, to have global scale applications. And that's where the idea of a microservice came from, is really trying to solve that problem. So instead of having a single deployment of software, they started breaking up software into autonomous components, where instead of software modules being all part of the same distribution, they would take a software module and deploy it independently and then wrap it up in some lightweight wrapper, such as an HTTP endpoint. And then you would have an application composed of a bunch of autonomous services that make up various parts of an application. So you might have a front-end service that's entire job is to just serve up static content to a browser. Or maybe that front-end service, its entire job is to be the API endpoint for a particular piece of the application. So it receives HTTP requests. But down here in the middleware services, I might have pieces of this application that do particular business-oriented tasks, such as do a particular kind of calculation, or maybe it's a supporting service like go send an email to a customer, or go write something to a file, or those kinds of things that get encapsulated in a service. And all of those functionalities are called by way of a network. So all of these little lines here represent a network call between various servers on a network. So you have a service that receives a call from a browser out here, it calls another service, and then behind the scenes that service might call another service. And then ultimately down here I might have another service that's doing data access, and it's returning data back and forth to another service. And so all of these various services create the application, rather than having a single monolithic application that is going to create your services and provide all the same functionality. Now, this has some advantages, main one being scaling, but it's also going to present some challenges. And that's really kind of the crux of what we're going to be talking about in today's webinar, is the challenges. But let's first talk about some of the advantages of doing this. One of the advantages is getting scale, and I've talked about this already. So traditionally, we scaled things vertically. Vertical scale has to do with basically increasing the size of your compute, basically adding more cores to the same compute, adding more RAM, adding more disk, making the network faster, making the CPU faster, making the storage faster. That's vertical scale. It's just making the hardware in a single compute node better so that it runs your application better. And that is what we call vertical scale. That's what we traditionally did in the past for scaling our applications. Now, what happened though is that the application scale outpaced what you could do with vertical scale. And so there were limitations to what you could deploy on the available technology at the time. So you need to come up with a way to distribute scale across multiple nodes. And so that's what horizontal scale happened. That's when horizontal scale happened. So what that basically means then is, instead of having a single compute node to run my application and making that single compute node run faster and faster, I distribute my workload across multiple compute nodes. They could be small or large, but the horizontal scale is basically just scaling my application load across multiple compute nodes, and I can just add more of those nodes as I need them for my application. Now, this of course comes with a lot of advantages over vertical scale, and the advantage mainly being that I can do a lot more elasticity in this. So as my demand on my application increases, I can add more nodes, or if as it decreases, I can remove nodes. And this is what we get with the cloud. So this is what we call elasticity, and auto scaling features typically will support this elasticity in the cloud, where I can scale up, scale down, and do all of those kinds of things with the scaling that I get with horizontal scale. And horizontal scale can also take advantage of vertical scale as well. There's nothing that says I can't have large nodes that scale horizontally as well. So you get kind of the best of both worlds with the story that microservices get. So I might have a microservice running here, one here, and one here, one here. And then that allows me to, but if I need more, I can add more nodes to my microservices and get more and more scale that way, rather than trying to cram everything onto a single compute node here. The next advantage that I get is easier upgrades. Now, with traditionally with monolithic or more monolithic applications, we did more of a service model where we did service updates more less frequently. We might upgrade once a year, or more frequently than that, maybe once a quarter, or maybe once a month if you did a patch cycle. But the bottom line is, you weren't really doing major upgrades on your system. You were very often you would do those major upgrades once a year. Usually you would go from one major version to the next. What happened with microservices, though, they realized that you could do minor upgrades to individual components because they're all deployed independently now. And so this allows us to do something called continuous integration. And that's basically where a given piece of code that is for a given service is being worked on. And then over time, you work on that code, and as you work on it, you're checking that code in continuously, and then you're running unit tests, you're doing builds, and then you're doing integration tests continuously on that same code base. And then what you do is you have maybe a build at the end of the week that you then take and you drop that into a release, and then that goes through an automation pipeline for acceptance testing, and then goes into a final production state with smoke tests. And what this this whole continuous integration, continuous deployment delivery allows us to do is upgrade individual components more frequently. And so this allows us to have software that's more evolving rather than just having these big bang upgrades with long periods of time between various versions. In fact, in many cases, the individual components of the application will be individually versioned. However, the application itself really never has a version that you might be aware of. It's what we call evergreen software. It's all the various components of it are always being upgraded, but there's no single overarching version that I could say, oh, it's on version 15. It's more like it's just evolving, and component X or component Y are on version 15, and component Z is on version 27. And it's just constantly being upgraded at the component level rather than at the entirety. And that's one advantage of having this approach with the idea of continuous integration and continuous deployment, because everything is broken down into the very small manageable components, and you can build and test and deploy those independently of one another. So let's talk about the next advantage, which is better availability. And this is with scalability, availability kind of comes with that. So the ability to have availability across in a high availability, not in just a single region, but multiple regions for an application, is something that is rather, I wouldn't say revolutionary. It's been around for a while, but it's becoming more and more common with applications as they adopt a more cloud focus, but also as they adopt a more microservice approach as well. And so what this allows us to do is have regional redundancy for a single application. And so you have typically an architecture that looks like this. You have some kind of DNS-based load balancing, an instance like Traffic Manager on Azure, and then you would have a region with front-end services running, and you would have a similar setup in another region. And depending on where the geography of the client is, they might go to this region, they might go to this region, and they will get better returns on speed because they're hitting something geographically closer to them. Or maybe this is because of something like a regional outage or something like that. Regardless of how you set this up, you basically have redundancy across regions so that you can not only support a region outage, say one region goes down, you can still have your application running in a given region, but it also supports that being geographically closer to the services, and it also supports scaling your application globally across a global infrastructure. And with the cloud, that becomes even easier to do because you're not trying to deploy data centers globally. You just take advantage of globally deployed data centers such as Azure, or AWS, or Google, and then you can deploy your application across that, and then you can get into these kind of multi-region schemes with your application and then be able to serve millions of customers that way. Or maybe it's not just millions of customers, maybe it's just they're mission critical and you need to have that for that high availability for your application. And that's important for some things that are running mission critical services like emergency management systems, things like software that runs hospitals and software that runs police departments, those kind of mission critical services that have to be up, that need to be running, and those need to be multi-region to get that going. And so they will adopt microservices to get this a better availability. So these are the primary advantages of this, but there's a lot of challenges that come with this. So when you adopt microservices, there's a lot of new challenges that you have to account for. And that's what I want to talk about through the duration of this particular webinar, is try to home in on some of those and then try to get through what those might look like. So the first challenge is state. So anybody that's ever written an application in microservices, one of the first things they have to deal with, especially if they're coming from a more traditional pattern, is how do I handle state? Because in a traditional application where you're running on a single server, state's just inherent. It's memory that your application, everything in your application has access to, and that doesn't happen whenever you begin to distribute your services. And you have individual autonomous services. I need a way to have state so I can manage that if there is state in my application. Now, The most ideal thing that you can do is make your application stateless. And generally speaking, that's a noble goal, but it's generally not possible. So what you do is you try to make the services themselves as stateless, and then you delegate the state to some other part of the application. You typically, and these are three different ways to do that. So we make our services stateless, and then we offload the state to something else. Now, there's two common ways that are done in microservices, with the middle one here kind of being a stopgap measure that's typically deployed for migrating applications or refactoring applications into microservices. This one right here, client managed state, this is where you have something like a browser involved. And the browser basically is responsible for maintaining the state for that given client. And what it will do then is it will create requests that have everything that is needed for that request to execute within the given service that receives it. Whatever API receives that request, the API will process it, return a response, and then forget it ever saw that client. And then the next request will repeat that pattern, and it never has to retrieve state from anywhere. Everything is passed with a request and everything is returned, and then the state is not maintained by any of the services. However, the client will receive that. It will maintain a state in the context of the browser's memory, or maybe it'll use some kind of local storage. In any case, the client is responsible for maintaining the state in that case. That's common with single page applications or mobile applications. It's a very common scheme for smarter clients that are running in the context of a browser or on a smartphone or a desktop application, if you're doing writing desktop applications to call backend services. Now, this one over here is very common if your client is not so smart, I guess. You might be doing this for more traditional web pages that are doing postbacks or things like that are re-rendering the page. This one, you might be maintaining state by way of a distributed cache. Now, distributed cache basically means that you take all the cache and you store it in something like Redis as a service, and Redis will be one of the services in the suite of services that you have available. And then what happens is all these services that need to maintain state or need to access state will go to that cache, retrieve the state for that session, and then it will be able to have that state for the duration of that request. And then if it needs to, it'll write the new state back to that cache. And then the cache then will maintain that state for a given period of time for timeout. Then it will purge it after a period of timeout, typically, an hour or 2 hours, whatever the timeout period might be. And then it will require that a new session be created and a new state be maintained for that session. Regardless, though, it centralizes that cache, and then you'll have multiple nodes of that cache copied. That's a very common scheme for folks that don't want to maintain state up inside the client. And this one's probably the most common approach. Now, a stopgap measure that folks typically do is load balancing and using sticky sessions. Now, what typically happens is in this case is where you have folks that start to break apart their monoliths into microservices, but they just can't seem to get the state out of their microservices or some piece of their code. So what they end up doing is implementing a sticky session. And basically what that happens is when a request comes in from a client, it injects a cookie into the HTTP request. And so that whenever the subsequent requests come in, it will always delegate that same client to a given instance of a given service. And the load balancer then is responsible for maintaining that sticky session. And so all the requests are handled by the exact same instance of that session. This is brittle, though, because it requires that you both have a load balancer that's smart enough to handle that. And it also makes it creates a single point of failure for a given set of clients. It might so if that node fails or that client or that particular instance of a service goes down, then all the state is lost for that given client. So generally, what folks do is use this as a stopgap measure until they can implement something like Redis to get the cache out of the client, out of the service itself, and then delegate that to a third party. A cache management system, or they put it back up into the client to maintain that state. But all three of these are used, and all three of these are different ways of maintaining state. Challenge number 2 is configuration management. Now, configuration management is one of those things that is difficult at best in a monolithic application. This becomes a big deal whenever you start talking about microservices, because with microservices, every single service has its own configuration. And what that means is it has to know where to find the dependencies that it requires to make it work. So if you can think about a configuration management, configuring any one microservice, it's got to know where to find the database or the data services it needs to access. If it's got external services it needs to call, it needs to know where to find those or how to reach those. And that's what configuration is all about, is trying to provide the component configuration so that the application can be configured correctly, and so that things know how to talk to one another, or settings or security settings, whatever it might be. And there's a couple of common patterns that are often used inside of microservices that make this work. The first one is a configuration service. Now, configuration service is basically what we call a well-known host. So you basically have one setting for all your services, and that's like, where is my configuration service? And then what happens is the configuration service will the service will go out and talk to the configuration service when it starts up, and it will get configuration data from that configuration service. So this is basically going to be like a key value store, something like etc. D. It could be memcache D. It could be Redis. Any of those work. There can also be some purpose-built services that do this, like Eureka and the Spring framework. All of those do basically the same thing, is basically key value stores that have setting information, and then this service then can go out there and request those settings from that well-known host and get back those settings and configure itself from that well-known host. So it only needs to know what that well-known host's endpoint is, and then it can get all the configuration data from that. Now, this requires more code, though. If you go about this way, it requires that you actually implement that as part of your code. Now, this one right here, platform storage, this one depends more on the underlying infrastructure that's supporting your microservices, and this is typically what containers do. This is what you're going to get with something like Kubernetes or something along those lines. What you then have is you have platform storage, such as shares or secrets, that are built into the platform. And so what will happen is the service will request some kind of data that is stored on the platform in whatever storage mechanism it's using, and that will be exposed to whatever the service will be at some kind of endpoint, and then it will be able to read that usually as an environment variable or as a file that's exposed to the service, and it's basically reading that from the platform storage, and then it will use that to configure the application. And so that's a very, like I said, very common with containers. So Kubernetes secrets would be one way to do that. Azure does this by way of app services. Sometimes if you're running applications in that way, you have a configuration pane where you can configure settings, but those are sometimes exposed as environment variables inside of the app services, or that you can expose config files by way of a mount, and then it can read those config files as part of that. Now, of these two, this one seems to be the more common one I've encountered, because a lot of the time folks are using containers for microservices, or they're taking advantage of some kind of platform feature to configure the microservices rather than doing it this way. This one's more common for purpose-built frameworks such as Spring Framework or something like Service Fabric. Even you can get configuration services that way. Now, another way that's commonly used is DevOps. And what this does is it injects the configuration at startup. And what that basically means is whenever at deployment. So whenever a service instance goes to deploy, the storage mechanism is going to be stored on the DevOps pipelines. And then what's going to happen is you're going to have a DevOps pipeline read the storage, and then it's going to read that storage and then merge it into usually some kind of config file, and then it's going to spin up one or more instances of that service by way of a DevOps pipeline, by way of some storage that's part of that DevOps pipeline, and the settings are going to be injected in as part of the pipeline, and then it's going to know how to meet the demands of the application by way of that configuration that was stored as part of the DevOps pipeline. Now, this one is gaining popularity in some cases because it allows continuous delivery to be and continuous deployment to maintain a lot of that configuration data for given environments. And while these have been more traditionally used in other environments, and in some cases, folks might implement one or more than one of these. And so folks might introduce a configuration service or platform storage, and they might use platform storage in conjunction with DevOps or something like that to get configuration data into the actual microservices that are going to be presented there. So challenge number 3 is service discovery. Now, this is one that is when microservices began to come on the scene, was a little bit harder to solve, and it was typically because the infrastructure methods of doing this with like DNS-based discovery hadn't evolved that much yet. It was done by way of typically done with a discovery service, and this was generally the same service as a configuration service. So it does something very similar to what a configuration service you would do. You have a service that gets service endpoints from a service. So the way this typically works is you have a service over here. What will happen is the service, when it starts up, it will present itself to the discovery service. The discovery service is a well-known host like the configuration service would be. And it will say, hey, I'm online now. Here's my endpoint. And it's typically the host name or the IP address of the given service. And it says, here I am. Here's my endpoint. And it registers itself with the discovery service. And the discovery service will have as part of its infrastructure, health checks, etc., to make sure that that guy is still online. Then you'll have another instance register itself as well. So you'll have those writing their configurations back to that discovery service. Then you'll have a browser make a request into some kind of endpoint. Now this endpoint needs to know how to find this service over here, but it doesn't know explicitly how to get to that endpoint. So what it does is it goes to the well-known host and says, hey, I need a service of type X. Give me an endpoint for service of type X. And it will return either the first or second or third endpoint, whatever it might be, back to this service right here. And then what this guy will do is say, okay, that's the endpoint for service type X, and then it will make the request to that endpoint. And then that's how, and if that fails, they can request an alternative route or something like that. So there's failover scenarios, et cetera, that are built into that. And if it needs to get a service endpoint for another service type, it will go and get that service type and then go to request that one. This one worked well for kind of some of the early iterations of microservices, where some of the other schemes that like DNS-based discovery weren't well supported yet. But in any case, it's still used, and it just requires that your services be more context aware of things and know how to reach those services. And it requires that everybody kind of know where the discovery service is, and that they understand how to talk to that guy. Now, a more common approach that is done more nowadays is using DNS-based discovery with smarter load balancers. And so what this does, and this is typically how containers work, and how other platform as a service implementations such as serverless will work. You'll use a load balancer. And what that does is basically it has a host name, and the host name is basically the endpoint for all instances of a given service type. So if it's my service type that goes and sends emails to clients, everybody that load balancer is going to have one or more instances of a service behind it. And what it's doing is doing health checks on those services to make sure that they're in a healthy state. And then it's going to be monitoring those services and scaling up and scaling down, etc., as part of that infrastructure. And then all that this service needs to know how to do is reach that load balancer endpoint, and it's going to be responsible for delegating out that request into one of the instances of a given service type. And so this one is very common with containers, and Kubernetes does this. This is typically how serverless approaches work, as well as APIs behind the scenes. And it's very common to use load balancing based schemes because load balancers are now evolving to the point where they can kind of do this as a pattern, and most infrastructure now supports it. And so this is becoming less popular while this is gaining popularity in microservices. So the challenge number 4 is interservice communication. Now, interservice communication is the communication that happens between services. This isn't so much concerned about clients connecting to services as much as it is services talking to one another. Now, there's a lot of debate as to how you should best manage this. Now, everything up to now that I've talked about is assumed that you're doing a more synchronous mode of communication. That is typically done over HTTP between different services. So you have a service calling another service. It's doing it in a synchronous manner. It's doing it typically through a load balancer. It's doing service discovery, and is making a request and expecting a response back to that request. Now, this that pattern works that works most of the time. However, there are some disadvantages to it in that if there is a breakage, for instance, that the service fails, the service request fails, you need to have a retry logic, or you need to have some kind of a way to load balance the request, or to get another endpoint for a different service. It can also create cascade failures that or have scaling issues. It's not always the cleanest way to do it. And so what more and more folks are going more towards is asynchronous modes of service calls, and that's typically done by way of queues and topics. And this is using messaging platforms like Service Bus on Azure, or messaging to platforms like MQTT or something similar to that. And what this does is with queues is you typically have multiple producers that write a queue, and then you have iterators on that queue. And so what this does is instead of waiting for a response, it just queues up a message, and then the message then is processed in time in an asynchronous fashion. If it needs a reply, then you can have a reply queue for the actual publisher of a message, and it can be listening to its own queue, and then you can have a correlation ID to correlate the messages between the request and the response using an asynchronous pattern rather than using a synchronous mode. And then topics do this similarly with one to many. So every time you write a message, everybody that's listening to a particular topic gets its own copy, and then it processes it independently of every other person that's subscribing to the same topic, while this is basically doing one-to-one between every message and every processing of that message. This is typically used to notify people when things change. Typically aren't expecting replies here. This one, queues typically though are wanting a reply in many cases. Sometimes maybe not, but many times queues are expecting some kind of response back to whatever is put in their queue, just so that, hey, I finished or I processed it, or something like that, just to acknowledge that it was requested, that the request was processed. This one, not so much. It's just saying, hey, something changed. I'm just notifying you. But in any case, both of these patterns are widely used for asynchronous communication, while this is using synchronous communication over here. More folks are preferring this, and this just tends to scale better, and it's also less brittle because it allows you to queue messages in the event that you have a breakage somewhere in your services, or something needs to be upgraded, or something goes offline. You can still process requests and queue them up while you're working to get this back end up and running again. So that's the inter-service communication. Challenge number 5 is security. Now, this one I want to talk about because this one is one of the biggest problems facing microservices nowadays, especially as more and more folks are getting away from trusted infrastructure and moving into zero trust. Trusted basically means that everything on the perimeter is secured, and you trust everything that's inside the perimeter. And so I only check credentials at the edge. And so everything like this client out here makes a request. Typically, it's going to be done by way of an authentication mechanism. It's going to go out and get some kind of token, and then it's going to pass that token with every request. And then the edge services are going to validate that token against some kind of security provider. That could be done through certificates, or it could be done through some kind of just challenge response type thing to a security provider to validate the token. Once the token is validated, then it just basically hands off the request to these internal services here without doing any further security checks on them. And so it just assumes that all these internal requests are already validated, already secured. Now, this is the approach that many service models have taken prior to the modern movement. Now folks are moving towards more of a zero trust model, and this one is inherently more secure because every request has to have a token associated with it. And so every request, it's validating the security of the request rather than just assuming that it is secure. And so as you move through these different security models, this one is gaining speed, especially in the modern age of where things have gotten exposure, because all it takes is one person getting something inside the perimeter here, and then it can make requests to all of these different services unauthenticated, and then it can expatriate the data outside the perimeter without having to do much compromise, without having to do much more than compromise the perimeter. Zero trust ratchets that up and makes sure that anybody, even if you compromise the perimeter, you still have to present a request or a token that has to be validated. And this allows me to, this model allows me to revoke certificates if I need to. It allows me to change the security model and allows me to have a lot more behind-grain control over security down to every service having to validate it. This one does require more thought, and it requires more strategic planning on the part of those writing the services, because you either have to implement this in the service or you have to implement this by some way of bolting on the security. And you can do that through things like service mesh with containers, but it's a little bit more challenging to implement than this one is over here, which typically just does it at the perimeter. But doesn't mean that you can't do this. It just means that you have to take some more planning on it. Throat's getting a little dry there. Now, the last challenge I want to address is probably the one that's going to take the longest to talk through. These first 5 have been pretty straightforward because they have dealt with some pretty common problems that are fairly easy to solve in and of themselves. Taking it as a whole, they're always trying to figure out which way I'm going to approach this in my microservice suite, but there are a lot of patterns. This last one, though, is typically the one that people struggle the most with, and that's dealing with data. And the reason why this one is so much a challenge is because folks, it's easier to scale microservices than it is to scale data platforms. And so if you start scaling out your data, your microservices, and you start to get these to multi-region, you got thousands of those. If you don't scale your data, that becomes the bottleneck in the whole system. And so you have to be able to scale it along with your data, along with your microservices. So you have to think about, how am I going to get my data to scale with it? And so traditionally, we've done things using the CAP theorem by preferring consistency and availability. Now, the CAP theorem is something that a lot of folks are becoming more aware of, but the idea behind the CAP theorem is that you basically have to choose 2 of these 3 things that we have here represented here. And what this basically means is that you have to prefer 2 of these while sacrificing another. And what the tension in scalability is not so much around partition tolerance as much as it is around availability and consistency. And there is a tension between these 2. So what databases have done is they have preferred what we call strong consistency and availability, while sacrificing partition tolerance. What that means is that once I write my data, it's immediately available. And that means that I can read it the millisecond later than I write it, and it's the exact same data that I wrote. And so as soon as my data, I like that strong consistency. As soon as it's written, it's available. So strong consistency and strong availability. And this is where traditionally databases have worked. And if you've worked in SQL, this is generally what you're used to. This doesn't scale well, though, once you get outside the realm of a single database. You have to start thinking about weakening your consistency or changing your availability. And you have to start making compromises between consistency and availability. And so what ends up happening is you end up weakening the consistency so that whenever you say, hey, I'm going to write something, but I don't expect it to be available to every node in a database the instant I write it. It will get there. It will eventually get there. That's what we call eventual consistency rather than strong consistency. It won't be immediately available, but eventually it will be available. So we weaken our consistency so that we can have performance, but it will not be available immediately. So this allows us to have global scale databases, because what I can do then is I can write a piece of data and then return a response, and then eventually that write will propagate across the global scale of the database, and it will become available to anybody that wants to read that data. And we're not talking about hours between the syncs. We're talking usually seconds. You might take seconds between a given write and a read that might not be consistent with that. So for some folks, that's perfectly acceptable. So if I'm Twitter and somebody tweets something, it's not mission critical that tweet be consistent across every single database, every single node on the data storage platform for Twitter for everybody to read. It will propagate through the system. Eventually, everybody will get a copy of that tweet across the globe wherever I'm storing that data. For other systems, that data, those kinds of strong consistencies become more mission critical. For some, that they need that strong consistency, and so they have to do other things to make sure that that data is available more rapidly. And there's a lot of different consistency models between that people implement to make sure that it's more available in a given region or a given subset of the data. Regardless, it's not black and white. So you have this kind of gradient between consistency and availability to make your database so that you can partition it across multiple nodes, and then you can scale it globally so that you can prefer that you can get into that partition. You can start partitioning that data, sharding that data across multiple nodes, that you can scale that data with your application. And so a lot of folks struggle with this idea of weakening consistency and making things eventually consistent so that and eventually available so that they can support partitioning across a globally scaling database. This is what MongoDB does well. This is what Redis does well. Typically, document databases do this well. The traditional RDBMSs like SQL and Oracle don't do this well, although they're getting there. There's some new technology that have been implemented in SQL that's getting to the point where you can get that eventual consistency going, and then you can scale it globally and so on. But these databases were more born in the cloud, so they can scale out better. Cosmos DB on Azure would be one example of this, where pretty much everything that you do on that data platform is going to adopt a consistency model that you can tune that will give you weaker consistency so that you can scale it globally, so you can partition that data out and have eventual consistency. It will eventually be available, but it allows you to partition it better, and so that you can scale it better, and it will scale more rapidly and more available, become more available across a global distribution of your data, rather than trying to keep it all centralized, so that you can have that strong consistency, that immediate availability across the platform. So this has huge implications on how you store data, and adopting eventual consistency also means that it's going to have implications on how you write services to access that data. And so data access in a microservice platform typically does not want to look like this. This is traditionally how we've done it, where we have a service, and every instance of the service is accessing the data directly. And this does not scale up well at all, because as you get more and more services going, you have more and more database connections coming in, and you end up taxing the snot out of this database as you grow those number of instances. This does not scale well at all. It becomes a management nightmare, and it's generally speaking, not something that you want to do with microservices. And so this is generally considered an anti-pattern in something like microservices. But I bring it up just so that it's a point of context where folks are used to dealing with accessing data right in the API that I'm dealing with. So I have a single layer that's accessing my data directly. Typically with microservices, you want to implement something that looks more like this, where you have a data access service that folks call. And this basically gives you a gate to your data storage. And so what you end up having here is an API exposure that's going to serve data to various other services that need to access a given database. And then what you end up doing is you might end up having multiple data access services, and with multiple databases as a part of that. And you end up with multiple databases as part of your platform rather than a single monolithic database. And what this allows you to do is distribute this database independent of this database, independent of this database. If you adopt eventual consistency and you adopt a model that supports partitioning, this becomes easier to implement, because you can have a service that is running its own database, as accessing its own database. That database is able to scale. It's more asynchronous. It's using a pattern that we're going to talk about in a minute that will support an asynchronous model, support a eventual consistency model without expecting things to be immediately consistency like we traditionally expected them to be in our given data access models that we've used historically. So using this indirect model by way of a data service that's entire job is to access service to other services is going to be what makes a microservice architecture scale better for data access. So to rehash, we're going to adopt for highly scalable models, we're going to adopt eventual consistency to provide to make sure that things aren't immediately available, so that we can adopt partitioning. We're going to adopt a model that uses a data access service, and then we're going to use a pattern in conjunction with that called CQRS that is using an asynchronous model to access the database. So typically we've done this right here with CRUD. We had APIs that did create, read, update, and delete. And those were typically using something like an ORM. And the ORM, these were just lightweight abstractions on top of an ORM. You'd say, hey, create is basically a database insert. Read is a select. Update is an update. A delete is a delete. And those mapped on well to SQL commands, and the ORM supported that. And that was a very popular way to do we used REST APIs to do this, and we used get, post, update, and delete to basically create a lightweight abstraction on top of common database commands that ORMs well supported. Not that that's a bad pattern. That works well for certain kinds of applications. With scale, though, this becomes harder to maintain. It just doesn't scale well for hyperscale applications. By that, I'm talking about data platforms that have to scale with hyperscale. This can generally get away for accessing data on an application that's going to be running in an organization, maybe with thousands of users, maybe with tens of thousands of users. But when you start to get into millions of users, that your volume of data is just going to be growing and growing and growing, and you need to scale that globally, this does not work well. You need a pattern that's going to allow you to decouple your reads and your writes, and you're going to want to be able to partition your data and tune that data more to scale across multiple partitions, multiple copies of that data, so that you can scale it more horizontally. And that's where this pattern comes in, CQRS. And that stands for command query response segregation. That's the pattern here. And basically what that means is your reads and your writes are handled separately, even in separate databases usually. So over here on the left, we have our commands. This is our creates, updates, and deletes. So this is data modification. So I have an API that exposes creates, reads, and updates. And then I have a domain model that does scrubbing on that. And then I have a repository right here that's doing data access. And this is in a write optimized database right here. And so all of the create, updates, and deletes are handled by way of this left channel here. And then what happens on a back channel here is I have a data sync to a read optimized database. And the read optimized database is happening asynchronously between the write optimized to this read optimized database over here. Simultaneously, what ends up happening is I have the repository inform some kind of messaging queue or topic or bus where I have an event handler that is reading changes that are going on. And it's basically updating clients. Things are happening. Things are changing in the environment. Here is, for anybody that's listening, here is something so there's a feedback loop between the changing data and people that are wanting to be informed of that changing data by typically a message bus. And this is also where my reads happen. So there's a query service over here that reads data. And so the queries go out to the read optimized data, query that read optimized data, and then return it back to the client. And so this entire model right here is based on asynchronous data access. Everything is happening asynchronously. Everything is using eventual consistency. This allows me to optimize my data for global scale. It optimizes my data for high availability. It optimizes my data to work alongside of global scale and high availability for microservices. So this right here, this pattern was devised as an alternative to CRUD to allow the database and data platform to work well with the microservices that need it, and so that it can grow alongside of the microservices that are accessing it, and you can have data that scales multiple regions, multiple platforms, and so on as you grow your data. A lot of times folks will grow their microservices without really putting much thought into their underlying data. They'll continue to try to scale this using horizontal scale while scaling their microservices, vertical scale, while trying to scale their microservices using horizontal scale. And they end up with a bottleneck at the database, and that ends up being a problem down the road. If you can adopt a model that adopts CQRS or asynchronous data access moving forward, as you grow your monolithic, as you grow your microservices, then it will scale with your microservices. So you have to be able to create a data platform to support it. This is probably, of the challenges that I've talked about, the biggest one that is going to be the hardest one to solve, because it's just, for so many people, a radical paradigm. They get the other stuff related to microservices, but they just don't get the data part of it, and they have a harder time changing their data access habits while adopting everything that's great about microservices without changing the data platform to grow with it. Anyways, that's what I'm going to say about that. So here's my list of best practices, just kind of summarize everything I've talked about up to now. Implement single pattern responsibility, refactor code to get away from sticky sessions. That's getting back. Use asynchronous messaging. Prefer indirect asynchronous data access with CQRS for data access. Prefer eventual consistency. That's just everything I've talked about. Leverage automation where possible for scaling, deployment, and configuration. That's getting back to all that configuration and service discovery I was talking about using DevOps. Preferred zero trust security to harden your security platform, etc. So that's just a laundry list of best practices summarizing everything I've just talked about for microservices. I do want to mention a few platforms here. We're almost out of time, but I do want to get to questions. So if you guys have questions, please pose those. This is just a summary of serverless. Serverless is a model where you can adopt a model of programming where you don't worry about state. or the underlying service, the underlying infrastructure. You just focus on the programming model. And a lot of the complexities that we've talked about are just managed by the platform itself, and you don't have to really think about it. High availability is one such thing. So this is handled automatically by serverless. State management is typically not managed by serverless, although you can do that. There's some durability that you might give us some serverless platforms, but in any case, if you need state, push that back up to the client or create a caching service to manage that with something like Redis. Configuration management is typically handled by the platform. Service discovery is handled by the platform. Generally using DNS. I said it's not handled. There's no built-in service discovery, but it's generally handled through DNS through well-known hosts. Interservice communication is typically handled by the serverless bindings that are available to the platform. Again, it's not something you have to put a lot of thought into because serverless provides so many different bindings that you can kind of bolt up a lot of different kinds of microservices built in a serverless model using things like messaging queues, or HTTP-based bindings that are readily available in most of the serverless frameworks that you have. So this is very easy to implement with serverless. Security is inherent to a platform. There's no inherent security to the actual code that you implement. Most of them have bolt-on security that you can do for authentication. So if you need to put on something like OpenID Connect and you want to validate tokens, you can bolt on security to your serverless platform, and it's just gonna, as part of the platform, it's gonna validate a token, check yes or no, this token is valid, and then it will grant them access. Although that doesn't do any kind of thing with role-based authentication. There's no inherent versioning built into this. It will need to be included. And data access for serverless prefers asynchronous model, the asynchronous models that we've talked about. So it's something that you want to consider if you're thinking about doing serverless as a way of adopting this with an approach to microservices. Serverless is a very valid way to do this. If I was going to write a greenfield application and it was completely new, serverless would be what I might go with, because I was going to adopt a specific cloud, say Azure or AWS. I would adopt their frameworks and I would go serverless because this one allows me to spin up things quickly, and it gets me a lot of abstractions for free without having to accommodate a lot of those challenges that are native to microservices. And this scales well. Everything I've talked about, it just supports everything I've talked about well for building microservices out of the box with serverless. Containers are a different story. These are used very widely in the microservice world, especially for folks that are kind of coming out of the more traditional models and they want to kind of refactor their code to reuse a lot of the code that they might have had in a monolithic application. Containers offer a great way to kind of get you into a place where you get a lot of the advantages of microservices by refactoring a piece of your code and then making it a microservice. And then you can use containers as a way to get a lot of the value out of a container platform, such as Kubernetes, to shore up a lot of the deficiencies that a monolith wouldn't supply. So Kubernetes supplies a lot of built-in functionality for microservices. So scaling, for instance, is handled by the platform. So instances scale across the available hardware that's available on Kubernetes. Infrastructure scales dynamically on infrastructure as a service. You can do that with like Azure Kubernetes Services. I can scale up and scale down dynamically as I want to. Built-in of high availability is part of this for the application. So containers have the ability to have built-in high availability because it's built into the platform. You can take advantage of that with your containers and distribute those across the available nodes that are available within your container platform. State management is not inherent to this, but it's easy to spin up with something like containerized Redis or using Redis on platform as a service. And it's easy to containerize it and use it. This is a common approach for containerized applications that are using microservices. Configuration management is done using Kubernetes as well. It does through Kubernetes secrets or through Kubernetes shares. That's one way to get data and configuration into Kubernetes. You can also use some of the distribution models that are available through Kubernetes to get this done, such as Helm and or config maps to use configuration management, and that also supports it. Service discovery typically uses DNS basic discovery. It's got built-in controllers for this, works well. Interservice communication is built into the platform, so it's got built-in networking, so it kind of normalizes that, and it provides built-in DNS so that you can get to service discovery, and so it brokers it in a secure fashion. If you want observability, you can bolt on something like a service mesh, and that'll also supply some of the security you need for it. And it does do HTTP ingress controllers that provide a lot of that security for things like SSL offloading. You can also do token validation and things like that. More robust can be implemented through service meshes that are bolt-on security as well, such as Istio. Versioning, it has controllers for that. It makes upgrading things easy. And containers support a versatile array of access. That's really up to you to implement that in the code. But containers, so because they're versatile, they supported a lot of different applications. So the microservice that you write will have to maintain that data access model that you adopt, whether you use CRUD or you use CQRS or asynchronous models for data access. So the last one I want to talk about is just using straight up old-fashioned APIs. Now, a lot of people kind of go cock an eyebrow and go, what is APIs? I didn't know you would use APIs to do microservices. You can use traditional APIs to do microservices. It is possible. You just have to do it a lot more finesse. Like with serverless, it kind of forces you to do a lot of things. APIs don't. So by APIs, I'm talking about things like web APIs through .NET Framework or something like that. Or if you're building these kinds of services, you can use those as microservices. You just have to have a disciplined programming so that you're not building monoliths and then calling them microservices. So you can build out APIs using Web API and distribute and adopt asynchronous patterns for your data access, adopt zero trust security. You can adopt all these things that we've talked about and deploy them in a highly available fashion, use state management, all these various things inside the APIs that you're going to be building, and deploy them on traditional workloads like IIS or Nginx or Tomcat, whatever the web server might be. But it requires that you adopt a discipline as a programmer to implement the APIs in a way that's going to support them as microservices. And you can deploy these on platform as a service offerings. You can deploy these on premise, but you can still use APIs to do microservices with. So that doesn't mean that, and oftentimes folks will use APIs and containerize them. And so it's not like this is independent of containers as a way to shore up APIs rather than host them in a more traditional model using a hosting platform like IIS or Nginx. So there are some things that I haven't talked about in this. Again, this has been a 1-hour presentation. It's been action packed. So let's see what we have in question wise. I just see what we have here. Let me pull this out here and see what we have here. I do want to answer your question. So thanks for hanging out for these extra few minutes here. First question is, yeah, that's my next slide. So first question is how is performance might you have with so many different services to get information? How is performance when you have so many calls to so many different services to get information? That's part of scaling. This is the first question. The first question is related to performance. That's part of what microservices is trying to solve. Is by scaling horizontally. The ability to scale horizontally means that you are able to handle the scale of so many different requests, how many different services calling other services, that the available capacity grows, and so that you have a lot of available network and compute and resources to handle that. That's why you scale that. That's why that horizontal scale is preferred rather than a monolithic scale. And that's why you are able to handle so many different kinds of services at once, is because you are scaling horizontally across a wider array of compute so that you can manage those numbers of requests. And so adopting microservices was designed to handle some of those performance characteristics where monolithic applications did not scale well under request loads. Horizontal scaling allows you to do that with microservices because you have the available compute to handle all those requests and handle all those services, because that's what that's getting at. Question number 2 is, can you give me an example of service discovery tools out there on the market? Service discovery tools, probably the one that is probably the best example I can think of is called Eureka. And Eureka is part of the Spring framework, although you don't have to use it with the Spring framework. It basically is the Spring. What it does is it gives you the ability to do service discovery, where any service, as long as it implements the API, can register itself with a service discovery, and anybody that wants to know how to reach an endpoint will reach that to service discovery endpoint, and it will get the data from it. You can also kind of fake it using just key value storage using something like Redis. It's very easy to implement using Redis. It's just you have a Redis key value store. Every new endpoint registers itself with a Redis endpoint, and then there's eventually a purge where after an hour it just removes it and requires that a service re-register itself every hour or something like that. So that's one way to handle it. There's a lot of ways to do that with it, but Eureka, the product called Eureka, is the one I'm thinking of. Next question is, can I have some more detail on serverless greater than data access, especially with CQRS in mind? Can I have some more details on serverless? Serverless with data access prefers CQRS. So let me back up on this deck here. Because CQRS is prefers this messaging platform. With serverless, you would want to implement your server, the create, updates, and reads, and the query itself will be implemented as serverless microservices. So this right here would be different serverless functions that you would write, or different lambdas that you would write for create, read, updates on the data. And then you would use repository pattern right here to update the database down here. This would handle this backend channel right here would be handled by way of a database sync between your write optimized and your read optimized databases. This would be a platform as some kind of as a service message queue, and then you would have an event handler here. This would be another service, another function, Azure function, AWS Lambda, whatever it might be, that's replying to this message bus, and that would be something that's handling that. That would be another function. That would be something that you would write in a serverless framework. This would be another serverless function that you would write in a serverless framework right here for querying data. And so you would it would query data out of the read optimized database. And so that's how serverless relates to the CQRS pattern. You would basically implement the CQRS pattern using the available technology you choose: serverless, Azure functions, AWS Lambdas, and then using something as a service for this messaging queue. And then you would use something that does a data sync here between a read optimized and a write optimized database with data syncing. So that's how the CQRS pattern relates to that. Let's see what we have here. Is it common for Cosmos DB? If I'm using my Cosmos DB for my microservice database implementation, do you think it's sufficient to tick all the boxes, or should I switch to CQRS? CQRS is not a database platform. It's a service. Like I said, it's a programming paradigm. It's a programming pattern that you would use. So like I said, let me back up to that slide one more time. This is all programming platform right here. So whatever database you use down here is really not the important part. It's how you implement this down here. I'm going to clean this slide up a little bit. Erase all ink. I can't. In any case, this is all done in code right here. This is all done. This is your programming pattern. The database is not the point. The database is just typically doing a read optimized, write optimized. CQRS would be done with a database technology. It can be Mongo, it can be Cosmos DB, it can be SQL Server. It doesn't matter. What you're doing is implementing an asynchronous model that supports an asynchronous data model. That's what CQRS is basically getting at. And so hopefully that answers your question there. So next question is it better? Is there a better alternative to using web APIs for communication for on-prem microservices? What about a cloud-based microservices? Is there a better is there a better alternative than using web API? I prefer using messaging platforms, like using message buses for that. I mean, just because whether it's on-prem or in the cloud, it's trying not to think of it in terms of locality. Think of your on-prem or the cloud as just different places for hosting microservices. So whether it's on-prem or in the cloud, what you want to think of those as just different geographic locations, and try to normalize whatever it is that you're using between those two. And then how they talk to one another is I would try to make that asynchronous using a messaging platform. So I would try to use, like Azure, you could use Azure Message Bus to do that. Or if you want to implement something like HiveMQ or MQTT, HiveMQ allows you to do some message syncing between on-prem and in the cloud if you wanted to do that. So you can have higher availability that way. That'd be something you couldn't do with something like a platform as a service messaging platform. But all of those platforms, what they allow you to do is basically just decouple the messaging platform from from one service calling another service directly. And I would prefer that for whoever's calling my services. It just gives me the ability to do things along those lines. So under what circumstances do full microservices fail in development and production, and how can this be avoided? Under what circumstances microservices fail? I'm guessing that the spirit of that question is, under what circumstances do they fail from just a technical perspective or from just an implementation perspective? That would be two different kinds of failure. But getting back to the microservices do fail. That's why they're built in. That's why you build in fault tolerance to microservices. That's why you do things like load balancing and prefer asynchronous patterns, is because failure is kind of assumed. And that's why you do that so that if they do fail, you have contingencies built into the platform so that your entire application doesn't go down. So where they typically fail in production is where you don't do enough testing. That's why you do CI/CD with microservices, so you get enough testing done. And then the failures will typically happen within the context of compute. Within compute nodes go down. But if you build your microservices well and you run them in a highly available platform, then what you end up doing is mitigating against failure. So you might have a node go down and you might have some requests that get lost, but your application's still running. And so you have a self-healing application so that maybe a node goes down, you can start redirecting requests to healthy nodes in that request. And so that's why you build in that high availability into the platform, and then write microservices so that you can create scalability and high availability into the platform itself. Under what circumstances do awesome session. I learned a lot. Thanks. I'm glad to present it. For real-time transaction services, does CQRS recommended? I'm for real-time. I want to clarify what we mean by real-time. Real-time is perfectly fine for CQRS. It depends on the consistency you need for the read of that data. If you're just processing data, receiving data and just processing data in real time and then posting the results of that to some dashboard, CQRS works fine for that, because you can do streaming through CQRS because of the pattern. CQRS, again, getting back to that pattern here, that pattern allows for right here allows me to notify when new data comes in. So if I'm processing data right here in my domain model, I'm processing data, I'm writing data to a database. I can notify people when things are happening. I can do real-time analysis on that data. I can do any of that. That is perfectly fine for real-time. CQRS supports that rather well. If you're talking about real-time access to that data within the context of availability, no, it's not really designed for that. That if you're like, I want to be able to read that data the instant it's written, that's not what it's designed for, because this again is asynchronous in the data being written and the data being read at the database. But if you're talking about streaming data and doing stream analytics, this pattern works perfectly for that, while this one's a little bit harder to deal with for that. It can work for that, but this one works well for real-time streaming analytics and that kind of thing. So that was that's my thing. Next question is CQRS better implemented for two databases? Isn't CQRS better implemented for two databases? As I recall, in DocumentDB generally offer best write times, while relational about querying. Here's what I would say to that. Database, don't assume that the database in the read database and the database in the write database are the same data in the same form. So this one is going to be optimized for reads. This one's going to be optimized for writes. There can be data transformations that happen in a data sync. So the data might be presented in a form over here that's optimized for reading the data. So you might be able to read it quicker. So I might do some denormalization in that data sync process. So this is not assuming like a data sync in the terms of a database copying data from one data into another. There could be data transformations that happen as by way of a data transformation engine, such as Azure Data Factory or something like that, that's doing data transformations that puts that into an optimized form for data writes. Data reads. So this might present it in a more tabular form that's optimized for reading, while this one's going to be optimized for writing data. And that's where so the database the way the data is presented for reading and the way the data is written are not necessarily the same thing, while the data sync process can transform that data. So that's just a way of looking at the data and how you can write those. So CQRS is really getting into a lot of the way that data is handled, and that what you're doing is basically separating the reads to the writes, so you can optimize reads, optimize writes, and so that you can not put those in the same bucket and handle them separately. So that's why we do that with CQRS. Last question, if you don't have any more. Thank you guys for hanging out for the last few minutes here for these questions. How can I debug my services in conjunction with other services without overwhelming myself with dozens of other services locally? Automation. Automation is the way to do that. So getting back to that, the slide, Vantage 2, this one right here. Everything that you want to do in this piece right here with code is, you want to be able to do all your testing, even over here, all your testing through automation. So with continuous integration, what the pattern is, what the pattern with the continuous integration is I'm constantly checking in code. All my tests are automated. So my integration tests, and even some people might do other kinds of testing right here. What they're going to do is they're going to have a deployment that goes into an environment that has all the services available in it. And it's going to have API calls. It's going to have a whole suite of tests that's going to run the gamut of everything that has that's available inside of my application through testing. And that's all automated. And so you want to be able to write good unit tests, write all your good integration tests, write all of your good test suites that you have available right here to make sure that you're not going to get overwhelmed with that. That's how you handle that, is through automation. And so that when I check my code in, I'm going to look for all the unit tests to run. It's going to do a build, and it's going to run a whole suite of integration tests against that to make sure everything's working right. So it's using that automation to your advantage to make sure that you're going to be doing that continuously. So continuous integration is typically done daily or bi-daily or even hourly if you want to get to that level where this is all automated. And that's the way that you can handle that without having to run a bunch of services locally. And so that's the way that's handled in there. All good questions. Thank you guys for hanging out. So if there's no more questions, thanks again, guys, for the great presentation. We'll be posting this onto our YouTube channel, and I'll put a link to the deck there, and for folks to review. And we're going to be doing eventually. There's going to be a white paper on this that we're going to be publishing. So stay tuned for our social media for that. That'll have a lot more details into this, and we'll have cover a lot more topics as well that I'm currently working on. But yeah, again, thanks for hanging out, and I'll be seeing you on future Winterlect webinars.